One day our friend Ku was struggling to understand hashing. And we get it, it happened to all of us.
Gavin, I need your help. Please! I need help! I need help with hash, please. Can you help me?
Bro, how did you get in my dorm?
Don't worry about that.
Okay, whatever. So you need help with hashing?
Yeah.
I guess to make it simple, we can use like a game to explain it. Do you have any games, Miller?
Fortnite.
Okay, let's do it.
I heard you need some help.
How did you get in here?
You don't need some.
As you can see, the items, in this case guns and heals, go to their respective slots in the inventory, but let's take a look at how this actually works.
So I can explain this one. So we often use a common hash function. So with our value being a number, we divide that number by the number of slots in the hash table and take their remainder and map it to that slot. We're actually using words and not numbers. We can use a formula to convert these letters to numbers so they can go into the hash function. For example, say we pick up this shield. We can convert the letters to numbers, A being 1 and Z being 26, and then do the hash function. So S is the 19th letter in the alphabet, H is the 8th, I is the 9th, E is the 5th, L is the 12th, and D is the 4th. So that adds up to 57. We have 5 inventory slots. So 5 goes into 57 11 times and leaves a remainder of 2, which allows the hash function to map our shield to slot 2.
So what happens if the index you want to put your item to is full?
I think I've heard of this one before. It's collision resolution, right?
Yeah, exactly. One form
I know this one. There's multiple forms of collision resolution. One of them is linear probing. When item gets mapped on a slot, but it's full. So it checks the next empty slot and then onto the next if it's also full. As you can see, when we try to pick up a rocket, which when we convert with our hash function, it gets mapped to slot 2. But since our slot 2 is full, it goes to the next empty slot, slot 3.
You didn't know anything about this stuff.
No, I was lying.
Why?
Oh, it's for the video.
Can you explain quadratic probing to me? I heard this stuff is like really complicated.
I don't know that one.
Really?
Yeah.
Okay.
I can do that one. So quadratic probing is pretty similar to linear probing. So if a slot is full, we can use an equation that outputs 1 plus x squared. So x is going to be the slot's index number. So in this case, we have our second index, slot 2. So if we try to map rocket to slot 2, but shield is already there, like what happened before, instead of mapping it to swap 3, we would do 2 squared plus 1. 2 squared would be 4, and plus 1 would put it in slot 5.
Is that all the types of collision resolution?
No, there's actually double hashing and separate chaining, but today we're going to stick to the basics.
Okay.
Lookup is an operation where the time and space complexity of O of 1 are constant. As when we want to find the value, we go to the key that it was assigned to, as well as allocating memory for that one space. To represent this in game, I can press 2 and instantly go to my shield, or here, press 5 and instantly find my rocket. So there can also be a case where lookup becomes O of n or linear, so this is the worst case situation. So this can happen when we use separate chaining with a linked list, which we didn't talk about that today, but it's basically just a list with multiple nodes you can put things in. So if you have to iterate through that is linear, time and space. You have to iterate through the linked list and allocate memory for each node. It could also be O of n if we use linear probing, a collision resolution technique, and we have to go through every slot in the hash table.
Now on to common operations and their time complexity. Insertion is O1 because it instantly inserts your value into the hash table using the key. Also allocates memory for the index we're inserting into. Insertion can also be ON or linear if we have to probe through every index to find an empty one to insert into.
Last operation is deletion, which is also constant time. Since we know which value is assigned to which key, we go straight to the key and delete the value, while allocating memory for that one index during this operation.